Okay, so let's continue our lecture. One more group we have. Actually, the second half of the lecture will be dedicated towards the subgroup part. Okay, group we have studied. Also, one more group we have this matrices group, general linear group, special linear group. We will also discuss about that in brief. That is very important group, in fact. After that, we'll be doing this subgroup part. Okay, fine. Let's start. So when I talk about just another category of groups, I will take just 5 to 7 minutes. Matrices. Okay. So for matrices, we have M comma M. This is a set, the collection of all M by N matrices. Let's say those entries are coming from some field, either R or if they can have some from C and all. Fine. So when I say whether this collection, this set, with respect to addition of matrices is a group, that is my first question. Okay, the other question is, let's say I have a collection of all those square matrices of order n by n such that their determinant value, or you can say this matrix is represented by A, you can say the determinant value of A is non-zero. What I'm saying, let's say this is represented by ZLNR suffix में R, LN suffix में R. If entries are coming from the complex field, we will see ZLNC, like that. For example, what I mean by it, let's say if I say ZL3R, what it will be, dear? It will be collection of all those 3 by 3 matrices with their determinant value as, okay, this is other category. Is it visible? Oh, fine. Third category is I have a collection of n by n matrices such that their determinant value is 1. I represent it is a SLNF, कोई भी field जो भी होगा, if we are taking from R, this is R. For example, SL3R, if I wish to write, it will be collection of those 3 by 3 matrices for which the determinant value is 1. You getting my point? So we have 3 separate categories here. Number 1, collection of M by N matrices. Number 2, collection of square matrices but with their determinant is non-zero. Very specific, determinant is not only non-zero but also 1. So we have these 3 categories. With respect to multiplication of matrices, okay, ZLNR and SLNR, these 2 forms a group. Is that clear? With respect to addition of matrices, this is a group. Getting? That means if you have some square matrix like that and their determinant is non-zero, is not given, then we will not talk about multiplication के respect में group, because as you know, A inverse is what, dear? Adjoint of A upon determinant of A. So with respect to multiplication, if I wish to talk about inverse, then I need to have determinant value as non-zero. Clear? So with respect to multiplication of matrices, we have two standard groups. Number one is general linear group. Number two is special linear group. This is just a subset of this. As far as addition of matrices is concerned, then with this composition and collection of all m by n matrices, that will form a group, but not with respect to multiplication. Is that clear to you all? So any example you can take. Let's say अगर मैं addition के बारे में just I will brief. Let's say I want to know A, B, C, D, E, F. What is additive inverse of this? So additive inverse of this will be, this is just a 2 by 3 matrix. This is just a 2 by 3 matrix. On addition, we will be getting a 2 by 3 matrix only. Also, this will be 0, 0, 0, 0, 0. So identity element with respect to addition of matrices composition of this group will be 0, 0, 0, 0 like this. Getting? Similarly, you can talk about inverse part with respect to multiplication. Getting? For me, to make you understand the things, please note it down. These lectures are not doing the Manrega Mazduri. These lectures are just smartly prepared where you people are confused, where I need to focus. Getting? Although I can take hundreds of hours of lecture by detailing, okay, अच्छा लग रहा है, लिखते हैं इसको. Not like that. Okay? So with respect to multiplication of matrices, see, if I multiply, यहाँ पर आ जाते हैं. I will change the color only. Let's say white. If I multiply two matrices with non-zero determinant, then their production will be also non-zero. So that means if I take any two elements of ZL and R, that means those two elements are with non-zero determinant. If I multiply those two matrices, A into B, so determinant of A into B is what? Determinant of A into determinant of B, and both are non-zero for you. So this will be coming out non-zero. That means if you take two elements, any arbitrary elements of this set, composition or multiplication of those two elements are also with the non-zero determinant. Order will also be same, n by n. So that means this A into B will also be an element of this GLNR or not? Because GLNR having what? Elements or matrices, square matrices of order n for which determinant is non-zero. So this is also a matrix. A into B is also a matrix of order n with non-zero determinant. So this will be again an element of GLNR. This is what? That multiplication of matrices is a binary composition on GLNR. Getting? Similarly, I can talk about multiplication of matrices. Always follow associativity in general. So this GLNR is nothing but a special kind of matrices only, na? So this will follow associativity. For inverse identity, GLNR will always have an element 1 0 0 0 1 0, similarly 0 0 1, n by n का identity matrix. Determinant of this I will be 1, that is non-zero. It means this n by n ka identity matrix will work as an identity element of this GLNR. If you multiply this matrix with any of this matrix, that you are going to get the same matrix itself. That means identity matrix will work as an identity element of this GLNR. Similarly, if determinant is non-zero, so by the formula A inverse as adjoint of A upon determinant of A, this will be always well defined. That means for any arbitrary element of this A, you have some element B in GLNR only, such that A into B is identity, determinant of A is non-zero, determinant of I is non-zero, so determinant of B will also be non-zero. Ultimately, we will be belonging to ZLNR. Am I clear to you guys? Fine. Similarly, I can talk about SLNR. Determinant of A is 1. Let's say A into B. I want to know whether A into B, if A is in SLNR, B is in SLNR, then A into B is also in SLNR or not. I want to check. So if I want to check A into B SLNR में है या नहीं, what I need to have? A into B का determinant must be 1. So if A into B, if I do A into B का determinant, it is going to be determinant of A into determinant of B. Determinant of A is 1, determinant of B is 1, ultimately it turns out to be 1. So what it says, if A is a matrix with determinant 1, that means A belongs to SLNR and B belongs to SLNR, then A into B is also in SLNR. Determinant of identity matrix is 1, that means I belongs to SLNR. So this is also identity element of SLNR. Multiplication of matrices follows associativity. So SLNR with respect to multiplication of matrices follows associativity. Getting? For inverse, let's say I'm not removing all those stuff because it is looking like good mathematics na. Let's say I want to know, let's say if A belongs to this element, inverse of A belongs to SLNR or not. This I want to know. So if B is inverse of A, then A into B must be identity matrix. And B is inverse. Now I take determinant on both sides. And determinant of A is 1. Determinant of B is 1 by 1, that is 1 only. Getting my point? Or you can talk about determinant of M inverse is 1 upon determinant of M. So 1 upon 1 is again 1. In any of the way you can go. That means with respect to multiplication of matrices, SLNR is a group. With respect to multiplication of matrices, ZLNR is a group. Is it commutative? Is it abelian? No. This is not an abelian group. Not ZLNR, not SLNR. But this is an abelian group. Addition of matrices follows commutativity, but multiplication of matrices need not be commutative. Make it a point. Fine. So this is all about this thing. Categories of groups. Now I hope I have covered well. Now it's up to you how you cop up with those examples. I'll suggest if you have any query, please do let us know in the comment section so that I can rectify your queries well. Sure. One more. थक गए क्या? मैं क्या यार इतना तो क्लास ले लेके ना हाँ टायर्डनेस आती है बट आई एम इन द हैबिट. ये 10 to 1 और 2 to 5 लेक्चर्स लेने के बाद 2-2 घंटे डाउट्स भी लेने का थोड़ा सा अनुभव है, तो 6-7 घंटे चलेगा, कोई दिक्कत नहीं. अच्छा, so category of groups are clear to you. Now we are moving towards subgroup. Here we will have some theorems as well. We will have the necessary and sufficient test to check whether it is a subgroup or not. Please, by believing on my way of teaching, you just try to finish it once. I'm pretty much sure at the end of the lecture, you will have very much confidence on this subgroup part. जैसे group में आ गया ना, the same I will follow here. But for that, you need to be patient. You need to follow word by word what I am trying to convey. So here I will have, see, as a student or as a teacher, it's always my preference that I need to know what is that peripheral in which I have to travel. So peripheral of the topic will make ना दिमाग स्टेबल हो जाता है कि यार इतना पढ़ना है, ऐसे ऐसे करना है, ठीक है. So एक तो डेफिनेशन होगा, दूसरा एग्जाम्पल्स होंगे, थर्ड वन विल बी वन स्टेप subgroup test, how to check whether a given structure is a subgroup or not, and other is bit important theorems. These two are important UPSC, CSE or IFS PYQs. Getting? So this is the peripheral for us. Now, subgroup definition. To talk about subgroup, we need to have some group first. To talk about Upendra, you first need, first my father ka existence will be there, na? So let's have a group Z, star. Okay. Let H be a non-empty subset of G. Please note down, non-empty subset of G. Now, with respect to same composition, if is itself a group. What I am saying, dear? H with respect to same composition is itself a group, then we say H is a subgroup of G. This is a representation or symbol for subgroup. Okay, we say H is a subgroup of G. This is the definition. For example, just recently what I discussed, ZLNR, what it was? Collection of n by n matrices with determinant non-zero. SLNR, what it is? Collection of all those n by n matrices with determinant value 1. Clearly, SLNR is a subset of GLNR or not? Also, we have proved just recently that this itself is a group. So what we will say, SLNR is a subgroup of ZLNR. That clear to you guys? One more example. S3 with respect to composition of functions, group of permutations. Let's say A3. This is alternating group, collection of even permutation. A3 was just a subset of S3. Also, A3 is a group. Then what we will say? A3 is a subgroup of S3. Moreover, AN is a subgroup of alternating group. Is that clear? Okay. Let's say Q8. This was what? Plus minus 1, plus minus I, plus minus j, plus minus k, such that ij minus j I k, jk minus kj is I. This is k. Ik is minus k I, that is j. I square, j square, k square, that is minus 1. So this is quaternion group Q8. Let's say I have some subset like 1 minus 1 I minus I. This is a subset of Q8 or not? Also, you can check it out with respect to multiplication. 1 minus 1 I minus I, 1 minus 1 I minus I. 1 minus 1 iota minus iota, minus 1 plus 1 minus I plus I minus I minus 1 plus 1 minus I 1 minus 1. From this composition table, H is a group. So H is a subgroup of Q8. Ready? So do practice at this lab. Similarly, okay, let's change the color. You tell me Z2 is a subgroup of Z4. Do let me know in the comment section whether is it correct or not. Okay. Can you tell all possible subgroups of Z with respect to addition? Like 2Z, that means set of even integers. 2Z is of the form minus 6, minus 4, minus 2, 0, 2, 4 and so on. If I say 3Z, means multiples of 3, 4Z, 5Z, 6Z. That is the beauty of reading this category of groups. Na? Once you have done that category, this all will be in a crystal clear picture in your mind. So if you talk about subgroups of Z, you will have MZ. What is this? Is not ZM. Don't confuse with this. This is MZ, means multiples of integers. This is always, MZ is always a subgroup of Z. Moreover, you can cross check. Acha, if you are interested, then check it out. 2Z is a group or not? So all possible groups of Z are MZ kind of. Okay? Any issue? This is interesting for you. Next, in the same fashion, you can discuss more examples of subgroup. So today's last topic is one step subgroup test. Very important, you guys. Please. Statement इसका लिखेंगे. Let's consider a group G star and H is a non-empty, underline the word non-empty, subset of G. Please, this is the necessary and sufficient condition you have to remember for your exam. H is a subgroup of, when I say H is a subgroup, means H is an algebraic structure, Z is an algebraic structure. If and only if for A belongs to H, B belongs to H, implies AB inverse belongs to. Please remember this statement, very important for you. Because with this statement, we will prove some theorems, some other results also. So please do remember. नेसेसरी एंड सफिशिएंट क्या है? If H is a subgroup, then this condition must be hold or necessarily hold. In other way, this condition is sufficient for H to be a subgroup of G. पलट के दोबारा सुन लीजिए. You will remember, many people are confused like this. Necessary and sufficient. Okay. So, if you want proof of this, let's do just one step only. Let H is a subgroup of G. This implies H itself a group. Getting? So, for A belongs to H, B belongs to H. If B belongs to H, तो B inverse भी तो H में ही होगा. क्यों? क्योंकि H is a group. So, A composition B inverse will be also in H. Why? Because of closure axiom. Because H is a group, so it is closed, or you can say this operation is a binary operation. Operation is what? Star. So if you compose any arbitrary two elements of H, again you are going to get the element of H itself. Is that clear to you guys? सबको? चलो. So that means if H is a group, then this condition will be necessarily holding. Other part is with interesting, right? Chalo. Other part is what? Let if this condition holds. What? A belongs to H, B belongs to H implies AB inverse belongs to H. Why I highlighted this word? There was some reason behind that. Since H is non-empty, so let's say A belongs to H and A belongs to H. This implies by the given condition A inverse must be in H. Don't confuse A into A लिख रहा हूं. A और A के बीच में कंपोजिशन है, whatever composition you have taken earlier for Z. A inverse is what? E. That means identity axiom satisfied. Any issue? Okay. Since A belongs to, अब देखिए इनवर्स की ओर, इनवर्स axiom. Let A belongs to H and I want to know कि A inverse exist करता है और H में है या नहीं. Since A belongs to H, E belongs to H, तो by given condition what it will imply? अच्छा उल्टा कर दे, इसको E ले लो, इसको A कर दो. A inverse must be in H. That means A inverse belongs to H. What happened? For each A belongs to H, we have A inverse in H. So H comma star satisfies inverse axiom. Inverse, after satisfying inverse, that means for each element of H, we have inverse in H. Now, let's say A belongs to H, B inverse belongs to H. Why I have taken B inverse? Knowingly, because from this condition only, what will happen? A, B inverse ka inverse will belongs to H. So inverse ka inverse is that element itself. So that means if you have A and B in H, then by second process we have shown that B inverse will also be in H. And since we have taken this condition as true, so A and B inverse in H implying AB inverse is in H, that means AB in H. This is what? Closure. So if this condition holds, I have shown identity in axiom, inverse axiom, closure axiom. What is remaining, dear? Huh? Associativity. अरे बच्चे, H के elements are coming from G only, and elements of G follows associativity because Z was a group. So H K elements will follow associativity. This you have to write in your, if you are doing proof, you have to write the fourth line, that since elements of H are nothing but elements of G only, so those will follow associativity. Combining all these four statements, we got H is a subgroup of G. That means this condition is sufficient for H to be a subgroup of G. That clear? Any doubt? I think necessary and sufficient का मतलब आपको समझ में आ गया होगा. नहीं आ गया होगा तो वापस जाइए वीडियो को देख लीजिए. Just I will take an example for this one step subgroup test and I will move on. One step subgroup test. Let's say वहीं से start कर देते हैं. अब तो अपने पास भरपूर मात्रा में राशन पानी है ना. VLNR, SLNR. I want to check कि SLNR is a subgroup of GLNR or not. So what I will do? The condition I will use, let A belongs to SLNR. अगर A SLNR में है, then determinant of A is 1. Let B belongs to SLNR. This means determinant of B is also 1. If AB inverse is also in SLNR, our job is done. So for that, I need to check AB inverse का determinant is 1 or not. So this is determinant of A into determinant of B inverse, that is determinant of A into 1 upon determinant of B, that is 1 into 1 upon 1, that is 1 only. This implies AB inverse also belongs to SLNR. So by one step subgroup test, what happens? If for A in SLNR, B in SLNR, we have shown AB inverse is also in SLNR. So it implies SLNR is a subgroup of CLNR. Is that clear? More clear? Is that fine? Okay, fine. आगे start करें क्या? चल, this is the lecture 1. Let's keep it finished here. Groups, subgroups, and subgroup के theorems. I am suggesting you guys to do a homework. The book I suggested, please note down some important theorems from there. 2-3 important theorems for subgroup part. Just remember, after doing all this exercise, I hope those proofs will be much easier for you guys. Okay, so you can do those proofs by yourself only. If you have doubt, do let me know in the comment section. Also let me know how these lectures are going on, either helpful or not helpful, so that teacher can improve. Improve करना है यार, इतने दिन से पढ़ा रहे हैं, it doesn't matter. Every time I am a learner only. So hope you will be enjoying more in the coming lectures. In the next lecture, we will be dealing cyclic groups, elements, order and all. Again, I will suggest, please remember all these structures, all these groups. Those will be very helpful to analyze or to visualize the concept. Okay. So till then, tata bye bye. See you next lecture में मिलेंगे.